Log on, tune in, find out. Another good idea from Cambridge.
Andras Szenes, welcome. He is speaking on calculating Thom polynomials.
Thank you very much for the opportunity to speak here. So I'll speak about the. So let's see. About calculating Thom polynomials. So this is an introduction of some joint work with Gergely. It first was done a while ago, but well, there are some recent developments. I don't know if I'll get to it. My purpose today is just to give you an introduction to this subject. It's a subject of enumerative geometry, which is maybe not as well known, as central as many others, but I think it actually has links with the current more current topics such as the Donaldson-Thomas invariance, etc. That's also why I became interested in it. So this topic was started in Thom about 50, 60 years ago, and it goes under the name of global singularity theory. So I will first just tell you what singularities are, even though you probably know. So I aimed, I don't know, at this talk at the non-specialists. I apologize if everybody knows what I'm talking about. So the idea is the following. Let's look at a map between two manifolds, M and N. So there will be some confusion. I hope I'll be able to explain why. So there will be two cases that for a while need to discuss in parallel. So these are either two holomorphic, it's a holomorphic map between complex manifolds, or it's a C-infinity map between two real smooth manifolds. So both cases are interesting. And the problem is that they're part of the subject that works in one and part for the other, and for pedagogical reasons it doesn't seem to be possible to eliminate either of these things. I mean, historically, Thom was looking at this, and I'll result say more in this framework. So it's a little difficult to not to speak about both. So I'll speak for a while in parallel with these two things. So the question is to classify the points of this map. So how to classify the points in M with respect to this map. And so what this means, so how do we do that? Well, we choose, say, a point P in M, and so then it has an image Fp in N, and then we choose a coordinate set here. So now just I will choose dimensions little m and little n here, and in this talk we'll assume that m is less than n. So so this is kind of the opposite of what like a function would be, like a Morse function. It's sort of these singularities I'm talking about is obstructions to immersions and things like that. So that's the topological background for this type of thing. So a lot of what I'm discussing is going to work in the opposite case when m is greater than or equal to n, but it has a different flavor in any case. Okay. Classify points in M. So then the way we will do that is that we choose points, local coordinates centered at P, so I'll denote them by xm, and local coordinates centered at Fp, so that will be y1, yn. And using these local coordinates, locally I can, so let's think about the holomorphic case. The other one will be analogous. I can write down the map as a set of convergent series. So basically it will be just a map that I'll denote by f check, which depends on p. I can put the p here. And this is a map from Cm, holomorphic map from Cm to Cn. Right? So sometimes you can also, what these maps are actually, this is a set of P1, Pn of power series in m variables. So each of them, I'll denote this set by Jm, so with infinite jets, and this is just, I'll think of them as power series in m variables, for which, sorry, what am I doing here? Pn. And variables which don't have a constant term, so that 0 I put there because they don't have a constant term, because I choose coordinate systems which are centered at these points. Okay. Now, immediately, just to, this is not at all necessary a priori, but immediately just to visually get rid of this infinite dimensionality, I point out one thing, is that we can, for the purpose of this talk, or of the subject actually, to cut down the infinite dimensionality and just look at this subset, which is then just the jets, the d jets of these functions. So this means I divide by all the monomials of degree at least d plus 1. And so this GADM is now simply, this is a nilpotent algebra. Right? Okay. And so I can look at just the image of this f check in this thing, which will be a little more easier to understand, at least because it simply is to every point I can associate an element of the nilpotent algebra. Okay, so now of course I made a choice, so this is not an invariant, so now I have to introduce the change of coordinates, and that is an object that's very similar to this f check. It's just it's going to be a power series just like that, just with m and n being equal, and such that the linear part of the map is invertible, right? So that's what a change of coordinates is. And now I can, this is a group, an infinite dimensional group, but again I can do the same thing. I can simply ignore all the terms of degree higher than d and obtain a finite dimensional Lie group. So this is a finite dimensional Lie group. Okay, and so this acts on our object. Yes, I didn't say yeah, finally I have just one more piece of notation I forgot to put here, which is that, yes, so these P1 up to Pn are here, and now our f check is a sequence of n of these things. So I have to introduce one more piece of notation, which is that f check P is thus in this JD of m going to n now, which is simply an n tuple of those elements. So this is, if you like, a d-jet of a local map, right? A very simple object. And this acts now on this GDMN. By changing the variables in the source, and so does diff n. So I have there's two commuting groups acting on this finite dimensional vector space, and there's a finite dimensional Lie group acting on it, and basically singularities are just the orbits of this action. So it's simply the quotient, the orbits of these two groups, right? So then this way I eliminated the choice of coordinates because I divided by the change of variables. Okay. So what this means is then, in particular, is that I can take if I have a map f m to n, then this induces something that I can call f sing from m to this set sing. Okay, let me put this little thingy here, sing d. Okay, so for every m, I can associate a singularity. So the question then, the topological question of singularity theory, which started, as I said, with work of Whitney and then Thom, was to understand this map. So if the topological study is to understand this, the properties of this map as we vary the map F in a certain homotopy class. Okay, so we are allowed, of course, you can have just constant maps, for example, and that's not so interesting. But let's look at maps in a certain homotopy class of Fs, and then let's try to see what this map F sub sing does. So, for example, a reasonable question: if given F and the singularity sigma in this sing D, does there exist an F tilde which is homotopic to F, such that F tilde sing inverse of this sigma is empty. In other words, can I avoid a singularity, a concrete singularity sigma in a homotopy class of F? So this was, of course, the one fundamental question of singularity theory. The simplest case is that here there's a very simple class in the sort of the top class, which is since now n is less than n, is just the smooth embedding, right? So if you like, there is the immersion class. So sigma 0 is the immersion class, which is represented by, if you like, by yi equals xi. So I'll write it in this f check as a set of equations for I equals 1 up to m, and then yi equals 0 if I. Right, so this is the immersion class. So, for example, if you, the generic behavior is probably this one, but the question is that whether, for example, if you want to ask about immersions, you can ask whether you can avoid all the other singularities in some way. So then the question is whether you can immerse one manifold into another. So this, as I said, this started before the war, I think. Whitney solved this problem in some cases. Theorem, I mean, there's, as you know, there's a bunch of theorems, but about the embedding theorem. But I'll just give the most basic, the simplest one that's relevant to us, which is not the general embedding theorem, which says that the question is the following. Let's try to resolve now. So I'll look at this RC infinity situation, and let's look at the case m equals n equals 2. Okay? So then, so this is a possibility. So I just have maps between surfaces. So the question is, what singularities do appear in generic maps? Okay? And the answer is the following. I think this goes back, maybe it's the term before the war. The answer is the following. So the same thing, for any f, there is a deformation into f tilde such that for every point in M, the corresponding singularity class f, well, if you like, f sing tilde p is one of the three cases. So one is well, here it's not immersion, it's just the isomorphism. So this is either has this form. Sorry, stupid things I wrote. The second one is the what's called the fold singularity. So that's this. And finally, the cusp singularity. So this. Well, anyway, I wrote it this way, and y2 is x2 cubed plus x1 x2. This one. So this is the complete classification. Oh, of course, there are many others. There's an obviously infinite set of singularities that you can present, but all of those you can just smooth out locally by just moving a little bit of your map. These three you cannot. Okay, and so these are the. And so essentially, one would like to have theorems of this sort for the general case classification of singularities that do necessarily appear. Study. So that's one question. So the questions I can now maybe more generally ask: what singularities appear, and if they do appear, for example, how to describe the locus of the places where these singularities appear in the map. Okay, so now it turns out that this is totally impossible. So it's just the singularity. So this is very nice when m is 2, but if you go beyond, I don't know, 6, for example, then there is not even any sort of hope that we will be able to describe even these orbit space. So of course the first question would be first to describe what this set is, and that is already not even known, I think, for like for any even not very large dimensions. Here the key numbers here is usually 7. I think that's where I get stuck in any case in everything I do here. So this is very, very difficult. It's a zoo, and all questions become kind of hopelessly complicated very soon. So we're just lucky that we live in these low dimensions when most of these things can be answered. I will introduce a simplification. So that's something that's called contact singularities. Contact singularity classes. And that's a simplification of this setup when but still infinitely complicated, it turns out. And the point is the following, is that there exists a map from sing D to nilp D, right? So to nilpotent algebras which associate to each this f check. So what we do, we have this f check described by this n-tuple of power series, which if we like we can divide by we can eliminate the higher terms, and then to this we just associate the algebra. This JD, as I pointed out there, this JDM is already a finite dimensional nilpotent algebra, and so we can divide this by the ideal generated. So ideal generated by these p's, and this will be a finite dimensional algebra, and that's an invariant that turns out to be independent of this diffeomorphism group action, so it descends to this quotient, and we can ask this. So several orbits, so many points go to 1 here, so this is not a 1-to-1 map, And this nilbd thing is also totally, I mean, it's also wild, so there is no description of all nilpotent algebras. Again, for small dimensions, it's very easy. For higher dimensions, then it becomes, they are moduli, and it becomes also very complicated. Okay? So here, I mean, so maybe, for example, we can just look here. So here, the corresponding algebra is just 0. Here, it's just the t. So it's just generated by one element, t over t squared. And here, it's t cubed, right? Because if I knock out x1 here, then I just get the third order. So this, in any case, this invariant, just taking the nilpotent algebra, differentiated already among these three singularities. And in general, the examples that we have are, for example, this called Thom polynomials singularity. Singularity class. So that's when I just, this product of any two elements is 0. So, well, put a 0 here. That's what I should have done. So, actually, I already introduced this notation, so like this. Okay, and so, and another example would be this one, which is called the AD singularity. And this is just the ones that appear here. So the object, the invariant, is remarkably simple, right? I mean, these algebras are very simple ones. Just t squared all the way up to t to the d. But the corresponding topology, as you will see, is infinitely complicated again. So, and this is what my talk is about. Okay, so so now I will get a little closer to what our research is about, and this is about this set here that I was discussing. So, for example, so now we have a map, right, given f, right? So we have a map which I can now call f, or not, I don't need this check, f nilp, which maps from M to this set of nilpotent algebras, right? And again, I can ask for the locus. So the question is, for example, what is the f, well, again, modulo some smoothing maybe, homotopy class f nilp inverse of a d. Say this algebra is actually, in a sense, you know, it's the longest one. In a sense, it's the most interesting one. So I look at this, I will close this, I look at as a subset of M, and this gives me a cycle. Right? So this is certainly, if everything was holomorphic, this is some analytic subvariety. So this is, again, over C now. And if I have this analytic subvariety has a class, and the question is to calculate, so the problem, calculate the class of this this class in M, well, in some, well, in terms of characteristic classes or characteristic numbers of M and N. Okay, so this is clearly a somewhat stronger thing that we could do here. Obviously, if we calculate this class, and this class, so this class, say, in the cohomology of M. If this class in the cohomology of M is non-zero, then it's clear that we cannot avoid this thing. Of course, it also involves the statement that this class is well-defined. It is. And if this class in M is non-zero, then clearly we cannot avoid this singularity, so it necessarily appears in our maps. Okay? So here it comes, of course, a point. After this is kind of smooth sailing, but here I need to somehow explain what I'm doing, because of course there is no such thing as homotopy of holomorphic maps. So I mean sometimes there are no holomorphic maps, for example, or there's various problems. So that's why sort of I need that C and C infinity business there. So the original problem, recognizing is that this was not considered to be a natural problem, was of course for the C infinity case. The C infinity case, however, the theory of these characteristic classes is not as rich as in the complex case, and also there's millions of technical problems. So as a result, so there's really, so I'll just write some comments here. So for the C infinity R case, actually there's obviously two situations: the mod 2 cohomology, which as a theorem of that I'll comment on in a second, which is well defined. So if I do all these things for over the real case where this homotopy business does make sense, then this indeed defines a cycle which will have a class in the mod 2 cohomology of M. So this is well defined. In the, so this is the, sorry, I meant here non-orientable. So then this gives you the mod 2 cohomology. And then there's the orientable. And this is really very difficult. So far, I'm working on this now, so I can tell that it's very hard. But the one problem is, for example, that it's not at all clear if you have an even algebraic subvariety over the reals that this will represent a cycle. So this is not so. It can have boundary, right? So and it's not necessarily orientable, and there's millions of other problems. So this is really very difficult. So classically, people looked at this. And in a second, I'll quote the theorem of Borel and Hafliger, which tells you that if I do the corresponding calculation of the complex numbers, that actually gives you the complete answer for this case. So the problem I'll solve will completely solve this one, and so it's after all, it's a weaker thing. So for that reason, we concentrate on the complex one. In a sense, it's a stronger statement. In the complex case, however, this thing doesn't make sense. So that's sort of why I have to explain myself. So I will explain now what we really do. Of course, so there's just many experienced people here with these kind of problems. One can think of this problem as an excess intersection theory problem, where so if the dimension of this cycle is greater than the expected one, you can still find this class somehow. Or you can take meromorphic maps, so there's a bunch of ways of getting around this problem. The fact that there are not necessarily sufficient freedom in choosing the map. But in any case, I will choose an even more straightforward solution for this problem, and this goes through equivariant Poincaré duals. So this is a very useful concept, which actually will give you a very precise terms and answer to this question, regardless of the fact that you cannot necessarily deform the map. If you can deform it, this answer will be correct. If not, this is what we take as an answer. And again, when you reduce it to this situation, it will give you also the right answer. So this is somehow some universal object that's easy to define, and which, in every case, which is necessary, gives you the right answer. Okay. So the equivariant Poincaré dual is also known as a multi-degree. Again, probably many people are familiar with this. Is the following story. So suppose I have let's for simplicity take a torus group acting on a vector space. So so the vector space is we assume that it's diagonalized, and so this is a torus group. So C star to some power, everything is complex. See? So we diagonalize this action, and then we just get a basis and a set of weights. So there is the weight of the action is in the Lie algebra of That's the weight lattice of T. So the dual of the Lie algebra of the torus. You have some weights. We'll not need this for at the beginning. So just this is the situation. And let's so W is a vector space, and let's assume that sigma is an affine, well, necessarily affine algebraic T invariant. And it's not necessarily that it's algebraic, but I'll just assume it for simplicity. Algebraic subvariety. So the equivariant Poincare dual of sigma is a polynomial, is a homogeneous polynomial over on T of degree equal to the codimension of sigma. And in a sense, this will be this is an equivariant characteristic class, and that's what we're interested in. So for at the beginning, I'll just give. It's not so easy to give a simple definition. I'll give you an axiomatic one, but then you don't quite see what's going on. So I'll give you an axiomatic definition, not completely precise, but and. So what you want to have is the following, is that this invariant is additive. So sorry, maybe before the other way. Sigma 1 union sigma 2 So this is additive.
Is that a disjoint union?
Yeah, sorry. So then this star is a kind of algebraic kind of disjoint union. So that, I mean, I didn't say very precisely, but what it is that you look at the top dimensional components of the variety, and there should not be common top dimensional components. It's a fundamental class, so we only care about the top dimensional common components, right? So that's what this is. And so shall I use that blackboard? Everybody see that one actually? I don't know. So so that's one property. So additivity. So then it's invariant under flat equivariant deformations. So that means this E, P, D sigma. So if I have a flat equivariant deformation, so it goes through invariant subvarieties and it's flat, then it's constant in T. And then there's a normalization. And that just tells you the case when this is simply an invariant subspace. So if I take an index subset, so sorry I didn't put here the number. So let's say it's a capital N dimensional, where this capital N is different from that manifold. So if you take an index subset here, and you look at then you can find an invariant subvariety, which is just given by the equations yi equals 0 for I in I. So yi, well, the coordinate yi, so corresponding coordinate y is 0. So the coefficient of y is 0. So this gives you a subset, and so this will be just the product of the eta I. Correct. Okay.
When you use generic, you may get some multiplicities,
Right. So I'm a topologist, so I sort of so that's why this is not completely precise. Yeah. So there is in one way of doing it, a simpler way of doing it is just to define those multiplicities, and then you have it for all schemes, and then it's better.
Right now, I don't know how to compute this, but if you told me what this polynomial is on twice that plane, then I would know.
Yeah. So it's twice that, because it's the additivity basically applies to that case as well. So this is not a definition. Sorry, I said it's a definition, but actually
In this additivity, you insisted that.
they don't have common components.
But it holds.
It holds then as well. Yeah. So I actually never quite looked at the. So there's also a topological definition which I use. It's not this one. This is the simplest one to explain. Yeah. So the simplest way is just to, from the algebraic geometer's point of view, is just to define multiple this for all invariant schemes, and then it's just then you have to define what this multiplicity is, which I was trying to avoid. You see, and because that's of course a little painful to do, not very difficult, but in any case, and then it is really a definition. Then you take a Grobner degeneration, and then you can just compute it directly, right? So that's actually one of the algorithms one would use to do this. So yeah, so really here multiplicities, and then it's better. Anyway, so there is an invariant like this. Okay, so as you see, so the simplest case is, for example, if you have just a linear subspace, then it's just the product of all the weights in the normal direction that you have, right? Because see, the degree has to be equal to the codimension of the. So, for example, it's a hypersurface, then it's just a linear polynomial. Okay, and so if it's a hyperplane, it's just one weight, and this one weight will be the only normal directional weight in the. Okay, so there is such a polynomial, and which is called multi-degree or equivariant Poincare dual, and so. What will be true, so there's just one little technical thing, if the torus is actually the diagonal matrices in GL, say GLM, so suppose, and sigma is now a everything is GLM invariant. So the action extends from torus to a non-commutative group. Well, still the torus does act. So this invariance still applies, right? So then actually, since I have a canonical basis, I can the polynomials on T as just a polynomial in M total M diagonal weights, the weights which are in the diagonal of the matrix, right? So this will be just a polynomial ring. So we're looking at a polynomial in this ring. And the little lemma that in this case, so in this case, meaning if the action extends to GLM action, then the polynomial, the multi-degree, is symmetric. So it's a symmetric polynomial. Okay, well, that's not very surprising. The while group starts playing a role here and permutes the weights, and so you get a symmetric polynomial. Okay. Now, once this is a situation, once I do have a symmetric polynomial, then in fact one little observation is that if Q is a symmetric Q in this C, and this ring is a symmetric, then you can define a characteristic, a universal characteristic class using it, right? So then for every, say, F and some bundle F over some manifold N, here we say this is a GL M bundle. We can define its characteristic class, which is can look at QF, which is in right? So the way we will get to topology, to cohomology rings from this invariant is exactly by the standard Chern-Weyl construction from symmetric polynomials to cohomology classes of bundles. Okay. Okay, now we'll need to erase. I hear this. Okay, so now I can get a little proposition which explains now how this whole fits together. So let's assume I'm somewhere here, and so let's take N, and let A be an nilpotent algebra, and I want to understand this cycle, and this F is, well, I'll have to assume, of course, now this transversality thing, which is not necessarily true, so it's transversal to this orbit in some sense, but it's not so important now what this means. In any case, this is a good case when this gives you the correct cycle, and I'll evaluate this cycle and I'll tell you what this is. Okay? Okay, so now I do the following. Well, I should have maybe did it before this proposition, this will take some time. I define what the Thom polynomial of this singularity is, and this is the following. So define the Thom polynomial of A. Well, you have to know this, the dimensions, so from M to N, is a polynomial in, so it will be a polynomial in some ways. So there's a definition in the middle of the proposition, if you like. Sorry. So it will be lambda 1, lambda M, and theta 1, theta N. So it will be in variables like this, and it's defined as the equivariant Poincaré dual of the of the cycle. What do I want to say? A, so sigma A in JDMN. Okay, with respect to the group of GLM, GLN in Okay, so what did we do? What have we done? So remember, so the original setup was that there is this set of map jets. So that with which I started originally, which I already erased. So maybe it's here. Yeah, so I can do this. Yeah. So here they are. So there is this JDMN. It appears here, on which this diff, the product of these two groups, acts. Now these are these substitutions, in which you have the linear substitutions as a subset, and in here now to every map jet there is this local algebra that you can calculate, right? So the local algebra only depends on this well, it's defined on this JDMN, and I look at those map jets who have the local algebra A that I fixed before. So this is a vector space, so this will be our vector space W, and there is among the map jets, there are the map jets with local algebra A. It's a subvariety that I can close if necessary. It's an affine subvariety, and for that affine subvariety, I can look at this equivariant Poincaré dual that I defined, and that's the Thom polynomial. Of course, Thom defined this 50, I don't know how many years ago, not knowing, of course, anything equivariant at the time. He defined exactly why this proposition. He proved that something like this exists. So I'll now finish the proposition. So I define this equivariant, this polynomial as a Thom polynomial as a as an equivariant Poincare dual. So according to this little lemma here that I said, this will be symmetric separately, permuting lambdas and the thetas, but of course not completely, right? Because now the action extends from a torus to a GLM and a GLM. And the GLM gives you symmetry here, and the GLM gives you symmetry here. Okay, so you get a polynomial like this. And so then finally I can, the answer is to, was, if you remember, to evaluate the cycle. So if you take the Poincare dual of this cycle now, f, well, since it's transversal, I don't put a tilde there. A, then this is, I close it, and this is now is simply equal to a cohomology class in M. And what is that going to be? That's just, so you see, if I have symmetric polynomials, so in this case, this symmetric polynomial is this. If I put in some bundles associated to GLM cross GLN, then I'll get cohomology classes. And of course, you can guess what those are. The M is simply T of M, the tangent space of M, and the N bundle is just the pullback by the map F of the tangent bundle of N. Okay, so this is not pretty complicated, but I hope I did it sufficiently slowly that after a while it can be deciphered. Okay, so in that sense, this Thom polynomial, which I defined this way, is a universal class representing the cycle. So again, if this thing that we compute now is not zero here, this means that this object is not empty, and that's what's our goal. Okay, so for that reason, these Thom polynomials are some of the universal. These are the characteristic classes of singularities, and they are also infinitely difficult to calculate in general. Okay. So, yeah, let me. I have 1 hour, right? I have to finish at 11. All right. So, our work is about calculating these polynomials. So, there's been a lot of work done on calculating these polynomials. It's Thom asked questions for various singularities, how to calculate them. This would also, it should include, in a sense, it will include, at least in some direction, Whitney's theorem for higher, partial results with respect to Whitney's theorem in higher dimensions, etc., etc. So now, what I wrote down now is exactly is only for complex manifolds. Okay. So now I want to make just a few comments on the structure of these polynomials and the relevance. So one point is the following: is that a TP A M N depends only on n minus m. So only the codimension matters. That's not very surprising. It's a fact. So again, of course, I didn't tell you what the dimension of the subvariety here is. That's an extra. It's also a calculation. It's not trivial. It's something. Okay. So there is this complicated subvariety of those n tuples of polynomials. When you divide by the ideal, you get a. That's what this thing is, right? It's something. But the fact is that it only depends on n minus m. There is a rather non-trivial thing which you could call the Thom-Damon theorem, which tells you that actually this polynomial in sort of two sets of variables can be reduced to a polynomial of one set of relative sets of variables. So that means that there exists a polynomial T D Thom-Damon A, so n minus m, but now it's in a set of classes RC1, RC2, RC, it goes to infinity. So it's a polynomial is an infinite set of classes, so the degree of RCI is I, if you like, 2i if you want in cohomology, such that this is equal to the Thom polynomial of A, so which is defined in these variables, these lambdas and thetas, which is symmetric. And these are the relative Chern classes of this map. So concretely, algebra, it's a very simple statement. It just says that I define a generating series RC of say t is equal to, so the generating series of this is sum of t to the I RCI from 0 to infinity. So RC0 is just 1. It's a constant. And this is just the product of 1 plus t theta j, say j goes from 1 to n, divided by the product of 1 plus t lambda, I don't know, m. No, now I will run out of letters. Well, I'll use I again. I going from 1 to m. Okay, so it's topology converted into simple algebra. If you want to know the Chern classes of the sort of the K-theoretic difference bundle between these two, then what you have to do is to divide these two points. You get a generating series, and then you take the coefficients of those generating series, these RCs, and those are exactly the Chern classes of the K-theoretical difference bundle. And the statement of Thom Damon is that, of course, not all polynomials, not all symmetric polynomials here can be represented as polynomials of these RCs. But the statement is that these Thom polynomials are such. So there exists this TDE, which actually, when you make a substitution, so you make this substitution, which I described here, then you, of course, so you, for each RC, you get some polynomials in thetas and lambdas. You substitute, then you exactly recover this polynomial that we are trying to calculate. Okay, and I think I'm forgetting something. And finally, I wanted to tell you about this Borel-Häfliger story. Borel-Häfliger theorem. And that tells you how the real and the complex, this that I mentioned before, how the complex and the real situation are related. And it's a very beautiful statement. I mean, it's hard to believe, but it's true that for the contact singularities are these nilpotent algebra invariants. So for this case, the following is true. So you can, of course, this proposition you can use as a definition of TP if it exists for these polynomials. And so Thom's theorem, the original Thom's theorem, said that this polynomial does exist, mod 2, in the mod 2 non-orientable case, satisfying exactly the same statement as here. Right? So you can just say Fmn. Now then there's a Thom transversality theorem that says that in the real case you can always deform F to make it transversal to whatever, so that this will be the expected dimension. And then this conclusion will be true. Okay, so in the real case, this is meaningful, so I'll call that RTP, say, I'll put, and so the Borel-Häfliger theorem relates the real and the complex Thom polynomial. So if I look at this RTP, A, then this will be, of course, in a polynomial in Z mod 2Z, sorry, this is really bad notation, but anyway, of R, and so now you have Stiefel-Whitney classes 1, R, Stiefel-Whitney classes 2, etc. So you have a completely analogous story, and you have the Stiefel-Whitney classes here, and I'll relate the complex polynomial to this real one. And so there is a map, the really stupid-looking map, which simply maps from C RC1, etc., to so now I have to be careful, Z RC1, etc. So Z2 RC R Stiefel-Whitney 1, etc. This is, I mean, makes no sense geometrically a priori. It's just the map, but the really obvious one, which is that RCI is going to R Stiefel-Whitney I. Okay, and you reduce the coefficients mod 2. Okay, so if you have an ordinary integral polynomial, the RCIs, you can you can just reduce the mod to. The reason I say it doesn't make sense because the dimensions don't fit. In cohomology, these are twice as big dimensional as these ones, so you kind of cut down the dimension. Nevertheless, what is true is that, so the theorem says that the Borel-Hafliger of the Thom polynomial, of the complex Thom polynomial of A, is actually equal to the real one. Okay, so this is really an amazing fact that is very special for.
Are these dimensions m and n there?
Yeah.
For the t.
Real, those are real dimensions.
they're
One is complex, the other is real. Yes. So they are the wrong dimensions. So these don't go in cohomology as the same dimension. Every dimension is cut in half somehow, but somehow this has to do with it. It's a real form of something. I mean, it's not at all obvious. Okay. So let me finish then with just giving you the result. So results. So first of all, there is what's called the Porteus formula, which many of you know, and that's really the A1 polynomial. This is a TP of the A1 algebra. So that's the AD was when you say TT, etc., to T to the D, right? So it's just the simplest possible singularity. Just says that it's singular. The A1 algebra is just from m to n is just equal to C of n minus m plus 1. So RC, I mean the relative Chern class. So I'll just write C instead of RC now. Okay. So it looks a little surprising maybe because the Porteus form looked a bit more complicated before, but actually that's exactly this statement. If you look this relative, rewriting this relative Chern class, then that's what it says. Okay. This is the Runge formula. That's for TP A2. This looks like this. It's Cn minus m plus 1 squared plus the sum from Cn minus m plus 1 plus I times Cn minus m plus 1 minus I. And there's a 2 to the I minus 1 here, and this I goes from 1 to somewhere infinity. But I mean, if it's negative, it doesn't make sense. So I don't remember now. So that was Runge form. That's from the 70s. And basically, up until about 3-4 years ago, there was no, or 5. These were the only ones that were calculated, really. So we found a general formula that now has been improved by Kazarian a little bit, but let me write down now I don't want according to that clock, right? So write down the formula for Runge's formula, which is in our form, and this looks like this. It's an iterated residue, meaning that you first it will be a differential form, and if you think of Z2 as a constant, and then you take the residue with respect to Z1. This is really just a type of generating series, and it looks like this. And here then you have this generating series RC Z1 RC Z2 times Z1 times Z2 to the power n minus m, and here there is a dZ1 dZ2. So it's easy to see that anyway. These are just it's 1 over. These are just some generating series. And it's this when you expand this series in the domain where z1 is greater than z2, then you exactly recover these coefficients, these factors of 2 here. Okay, so I don't know. And so, so this was just rewriting Ronga's formula. And well, let me just, I don't have much time, 1 minute, so I'll just write the rank 3, which wasn't known. Okay, so for that case, it looks like this. Tp of A3 is, again, so now it's the iterated residue, a triple one. So Z1, Z2, Z3, all taken at infinity. Here you take the Wundermann, so Zi minus Zj, and here you take the product of all things where the sum of the indices, so 2 pluses and 1 minus, and the sum of the indices of these are less than here. So that will be 2z1 minus z2, because 1 plus 1 is less than 2. You have 2z1 minus z3, because 1 plus 1 is less than 3. And you have one more, which is z1 plus z2 minus z3, because 1 plus 2 is less than 3, less than equal to 3. And the rest is just the same thing as here. So it looks like this. It's the product of Rc 1 over Zi. So it's a product from 1 to 3. And dzi times z to z n minus m. So just the standard generating series. And so it would have been great if it continues like this. So I gave you a prescription for the numerator and the denominator, and this always remains the same. But of course it doesn't. So as you progress, these factors remain, but there is a new polynomial q appears, which now I don't have time to define, but maybe anyway for the rank 4 case. It's so this continues like this for it always has this form for any d, where you change this to d, and so the point is to calculate qi and determine what it is. We found a very nice description for that, which I'll omit now. I'll just give you the sequence. So q1, q2, q3 is equal to 1, so then there is no q, but for q4 you already have a linear thing, which I think is something like 2z1 plus z2 minus z4, something like this. And this is an equivariant Poincare dual of a certain subvariety in a representation of in a closure of a Borel orbit somewhere, which can be calculated relatively easily for up until say 7, 8. So then finally we reduced it to some other problem, which is also not very easy to calculate, but still, I mean, this is a big progress nevertheless. You understand the structure, and we really understand the essence of where the mystery really is. Okay, so I'll stop here.
So the Porteous formula has obviously its analog of the degeneracy also have vector balance, which is used a lot in algebraic geometry.
Yeah.
So how about these higher ones?
Yeah, so this is all the same thing. You see, the problem, it's hard to now to explain it precisely, but of course, the way the general loci appear here is simply because you have these two. It's really when you have a map from M to N, you have a map from the tangent bundle to the other tangent bundle. It's you get a bundle map, and it's the degeneracy loci of this map is what a singularity is in first jet. And you have higher jets, then it's a little slightly different flavor, but it's a singularity is a degeneracy loci, but a more complicated thing. So maybe just I want to say one comment of what this is related to is you see, to have like an AD singularity is sort of is to have a d-jet of a curve in your manifold on which so if you have M, and n, now you have this map F. So if this is lower dimension this, so to have a degeneracy just means that you have a tangent vector here which goes to 0 here. That's what a singular point is, right? So if n liter to n. So normally it's an immersion, but if it's not an immersion, there's a direction which goes to 0. Okay? And the AD singularity, for example, means you take spec of AD, it's a d-jet of a curve. So that means there's a d-jet of a curve here. So I don't know how to draw a d-jet, but it's basically a curve of a curve which goes to 0 in this map. That's the kind of degeneracy we're calculating. That's much more complicated than the usual. It's not linear algebra anymore. And from the point of invariant theory, if you know why it's very complicated, because this has to do with alternatively either the diffeomorphism groups, these div-Ds, which are non-reductive. So, and then we don't know anything about non-reductive groups usually. I mean, it's very difficult. Or you can think of it as this I didn't explain, but dividing by the automorphism group of this d-jet of a curve, which is a quotienting by a non-reductive group again. And that is, again, that's essentially the problem we solved in some sense. So this quotienting with respect to non-reductive group, and then calculating some invariance in the quotient. So this quotient you have to construct by hand then, and apply some localization principles. And it's quite complex, but this is the kind of formulas which resolve. Okay.
Any other question? We have a second talk at 11:30. Let's thank